Okay, and we're back. So we're going to pick up where we left off. Alright, so we were going to do some examples with the Euler-Lagrange equation, which we just derived above. And the first example we're going to do is the shortest path between 2 points. So this was the first thing that we did in this chapter. In that case, since we've already done some of this, I might just show you that in the interest of time. Alright. So what we've already done on this problem is we've stated the problem, 2 points, x1, y1, x2, y2, in a plane, path y equals y of x connects them, which y of x gives the shortest path. And then the next thing that we did was, for a general path, write an integral for the length of the path. And so the increment of length for an infinitesimal bit is dx squared plus dy squared, where we notice that dy is equal to the derivative of y with respect to x times dx over this infinitesimal length. So that's y prime dx, which makes ds the square root of 1 minus y prime quantity squared, quantity times dx, and the total length would be the integral of that. So I'm going to pick up from there. Okay, so that's the expression that we're starting from. And then I notice that this is an integral quantity, and that I want to know where its minimum occurs, so where its derivative would be 0 with respect to that alpha, where alpha is the sort of perturbing factor that multiplies the change function that's added. Anyway, so I'm sort of making up terms for that now. But anyway, so that will be equal, the derivative of that with respect to alpha will be zero when the derivative of this object with respect to alpha will be 0. And as that was the basis of our derivation of the Euler-Lagrange equation. So this is the condition for which this object, the integral, will be minimized, is when the integrand is minimized. And so this is the expression for that. Okay. So in this case, I have a function, and I still have my independent variable as x, so I have y is my dependent variable, and obviously y prime comes into the expression as well, and x is my independent variable. So this function here, that integrand, is my f, so it is 1 plus y prime squared to the 1/2. So what does that mean? That means in order to apply the Euler-Lagrange equation, I need to consider 2 different things. I need to consider the derivative of f, the partial with respect to y, and obviously there is no y here, so that's 0 because this is a partial. And I also need to think about the partial of f with respect to y prime. And so that gives me the derivative of this object with respect to y prime, so that's 1/2, 1 plus y prime squared to the negative 1/2 times 2y prime. Just with our product rule. Okay, so what page am I on here? Hold on. Alright, so for this is still page 1. Alright. Okay. So when I apply the Euler-Lagrange equation, so I have df dy minus d dx df dy prime equals 0. And obviously obviously this applies for f, which is a function of y prime, and x. Okay, so this whole thing here is the Euler-Lagrange. Okay. Alright, so I'm ready to plug in. For my particular expression, I get 0 minus d dx of, I'm going to get a cancellation there, so I get y prime times 1 plus y prime squared to the negative 1/2. And that must be equal to 0. Okay, so this is, when I apply the general Euler-Lagrange equation to this particular case, this is the expression that I get. And this expression will hold so long as this argument here is equal to a constant. So I can rewrite this condition as y prime, let's say, divided by 1 plus y prime squared is equal to some constant. So just some stupid number, 4, 2, whatever it is. Okay. So now I need to solve for y prime. And let's see what I get. So I get y prime is equal to c times the square root of 1 minus y prime squared. I'm going to square both sides. Y prime squared is equal to c squared minus c y prime squared. And I get y prime squared times 1 minus c, hold on, I squared that, so that should be squared as well. 1 minus c squared is equal to c squared. Oh, I'm putting that, I'm making an error here. So I've got y prime squared. Yeah, that should be a plus sign here. Hold on. Oh, there's the sign error that I had. I apologize. I dropped a plus sign and turned it into a minus sign. That was a plus sign there. After I squared it, that makes that a plus sign. And y prime squared. And so now this is the correct expression. Okay. C squared equals c squared. Alright, so y prime squared is equal to c squared over 1 minus c squared, which itself is also a constant. Let's call that c2. And that means that y prime is equal to a constant. And that is a straight line. And yeah, in theory you should have plus or minus there, but nonetheless the slope is equal to a constant, whether it's a positive constant or negative constant. Regardless, we have a straight line. So the shortest distance between 2 points, it turns out, is a straight line. Good to know. Alright, so the next example we're going to do is a really cool one. But before we do that, we do need to talk a little bit about variables. Alright, so so far in what we have done, our variables have been y prime, and x, where y is our dependent variable and x is our independent variable. Okay. So, and what I mean by that is that that y therefore is a function of x, and obviously so is y prime. Okay. Now, generally for one-dimensional motion, we are going to have our variables be x prime, and t, where x prime is our derivative with respect to time, also known as x dot. So we should note where in this case we have x is our dependent variable. T is our independent variable, such that x is a function of time. And obviously, in this case, x prime is x dot. Okay. And that will be coming into play more in the next chapter when we start thinking more about motion. But there's one more example I want to do in this chapter before we do that. And in this example, so just for the following example, we will use the variables x, x prime, and y. Alright? Where y is going to be the independent variable. That's not what I want to say first. We'll say x is the dependent variable. Y is the independent variable. And ultimately, we'll have x will be some function of y, and x prime is the derivative of x with respect to y. And that will be what we're seeking to find. Because you can describe a curve in space either by expressing y as a function of x or x as a function of y. It will make sense to do it in this fashion mathematically. It will be simpler. And so we're just going to know that in advance. And let's get started. Okay, so the example that we're going to do now is the brachistochrone. It just doesn't roll off the tongue, but the brachistochrone. All right. So what this means is that we're trying to find the path of the least amount of time. So let me write out the statement of the question. We're given 2 points with point 1 being higher than point 2. In what shape would we build a track for a frictionless roller coaster such that a car released from rest at point 1 would reach point 2 in the shortest possible time? So such that car released from rest at P1 would reach P2 in the least amount of time. Okay. So in this case, let me draw a figure of the situation. We're going to make a coordinate system, and it's going to seem a little bit odd, but there's a reason we're doing this, and the origin of my coordinate system is going to be P1. This is the x direction, and we're going to go ahead and call down the y direction. And here's the point P2. Alright, so if I want to figure out the time that it takes to go from P1 to P2, I need to integrate over increments of time, such that a small infinitesimal increment of time would be the amount of time that it takes to go this tiny increment of distance along the line. So this amount of distance here is ds, which is dx squared plus dy squared, quantity square rooted, which we'll use in a bit. And the thing to remember is ds is also equal to v times dt. So if I want to have an expression for dt, it would be in terms of ds. So let me give you an example of that. So let me just go ahead and write the expression. So the total time to go from point 1 to point 2 is going to be the integral from 1 to 2 of dt, which equals the integral from 1 to 2 of ds over v. Alright, so I've got my expression for ds. That's not the exact form that I'm going to want to use, but now I also realize I need an expression for v. And so for that I'm going to use the fact that this is frictionless, so no non-conservative forces are doing work. E final will be equal to E initial. And so I'm going to have E final to just be some arbitrary time, and E initial will be E1. And this is my conservation of energy. Alright, so at some later time I'll have Ke plus Pe. I'm just going to go ahead and skip that line. 1/2 mv squared plus a what do I want to say there? Negative mgy, because y is going to be this number, so alright. And make sure that I like that symbol. Yeah, I think I need that. Okay, and that'll be equal to, now initially it's at P1, which is where y is 0. So potential energy is 0, and it's at rest, so that's just 0. My m's can cancel out here, and I get that v is the square root of 2gy. So that's fine. I can make that substitution. So from 1 to 2, ds over the square root of 2gy. But now I need to also think about this ds. My independent variable in this case is going to be chosen to be y, because this is a function of y that I have to integrate over. So that's why I had to choose that independent variable, because the y turned up in there. So when I think about using that as my independent variable, then I can rewrite dx squared as dx dy times dy. ds equals dx dy times squared times dy squared plus dy squared, quantity square rooted, also known as dy, well, this is x prime squared plus 1 quantity to the 1/2 dy. Okay. Alright, so now I have this expression for ds that I'll make my substitution here. So now I'm integrating from y1 to y2 of x prime squared plus 1 to the 1/2 over square root 2gy times dy. Okay. Alright, so this is pretty much what we want, although I want to go ahead, if I can, and make it the simplest math I can. So I'm going to pull out my square root of 1 over 2g up front. So then I just have sort of x prime squared plus 1 to the 1/2 over square root of y dy. And this object in here is my integrand. So that I want to, that I will get the minimum value of this when this integrand is minimized. And that function is, let's remember, that's a function of x, x prime, and y. Alright. Because now we're ready to apply our Euler-Lagrange equation. So I always, you know me, I write things out in their original form first. So the Euler-Lagrange equation is that the partial of f with respect to y minus the partial with respect to x. I don't remember if that is a partial or if it's a full. No, it's a full. d dx partial of f with respect to x prime equals 0. This was the condition for the minimum integral. And in this case, we had our expression of f was a function of y prime, and x in terms of dependent, the derivative of the dependent with respect to the independent, and the independent variable. So now here, I don't want to use that general form. I want to use the specific form for this problem. So I have to put my, wherever I see y, I need to put my dependent variable. Wherever I see x, I need to put my independent variable. All right? So I've got, and you know what? I made an error in writing it. Sorry. I think I probably said it right and wrote it wrong. Okay. So wherever I see y, I need to put, in this case, well, let's just make it, I'll go ahead and do it. So in this case, wherever I see y, I have to put an x. No, Libby. Okay. All right. So that's the expression that we get now, because wherever I saw it, this holds for f is a function of x, x prime, and y. All right? So that's the expression that we have to use, and so there is the function itself. So let's go ahead and do it. So, and I'll go ahead and write where that function is. Let's go ahead. X prime squared plus 1 to the 1/2, y to the minus 1/2. That just makes it easier for me to do the calculus. All right, so let's go ahead and do it. There is, for the partial of f with respect to x, I get a 0. Minus, and this should be a full derivative. Derivative with respect to y, df dx prime, so that will give me 1/2 x prime squared plus 1 to the minus 1/2 times 2x prime times y to the minus 1/2. Now let me look at that and make sure I haven't made any errors. Okay, and then on the right hand side I still have my 0. Okay, so in order for that to be equal to 0, this is again kind of an easy one because this term here was 0, one of the terms is 0, so that tells me that this whole object here must be equal to a constant. And, you know, your book says, well, we're going to call that constant 1 over the square root of 2a for simplicity. That's fine. I can buy that. I'm not going to do it exactly the way that your author does it, so this won't be very convenient for me, but it is still sort of somewhat conventional to use that. Okay. So, in this case, I have to solve for that. So I've got x prime. I'm going to go ahead and square both. I cancel out my 2's, square both sides, and I get x prime squared. And that is equal to square root of 1 over square root of 2a. I'm going to put everything else on the other side. Times y times x prime plus 1. I'm sorry, x prime squared plus 1. Alright, so what I did was I multiplied. I got x prime sort of alone on one side, kind of, although it's on the other side as well, and then I squared both sides, and I get this expression. Alright, so now I still do want to get x prime all alone, so let's do that. So I have, I'm going to go ahead and multiply this out. So, got x prime squared is equal to, oh, and I didn't square my 2a. It should be 1 over 2a without the square root. Alright. Now let me check, because now I think I squared that side and got that, squared that side, got that, and multiplied by both. All right, I'm okay. All right, so let's keep going. So I've got y over 2a x prime squared plus y over 2a. So I've got x prime squared times 1 minus y over 2a is equal to y over 2a. And x prime is equal to, let's square it first. So I've got y over 2a times 1 minus y over 2a. I'm going to multiply numerator and denominator by 2a, and I'll get y over 2a minus y, which is fine. So that x prime is equal to the square root of y over 2a minus y. So now, in terms of what I was looking for here, I don't have x as a function of y. I have the derivative of x with respect to y. But if I want x as a function of y, then I am going to have to integrate. Because this is dx dy. Alright, so in order to get x, I'm going to have to integrate. And here I want x as a function of y, by the way. From y1, which by the way is equal to 0, to y, which is just sort of an arbitrary y. The square root y over 2a minus y dy. Your author does some very nice analytical mathematics here. I'm not going to expect you to use your time on that. I would just as soon have you put this into Wolfram alpha, which I have done, and it gives a very messy function, which I will give to you now, but it came from Wolfram alpha. Alright, so here is our final answer. And by the way, this is I've obviously just multiplied by both sides with dy and integrated from y from point 1 to an arbitrary point. And let's remember that x1 is also equal to 0 because that's the way I chose it. So that would be minus 0. So if you're wondering about that math step, hopefully it makes sense to you. Alright, so let's go ahead and just report the answer here. 1 over the square root of y times the square root of y over 2a minus y times the square root of y times y minus 2a plus 2a. I'm going to get short on space here. Square root of 2a minus y times the inverse tangent of the square root of y over 2a minus y. Alright, so that's the expression that is what this function is. It's a function of where we are plotting x as a function of y. Alright, so now we can get that exact shape, and its mathematical form is here. Alright, so obviously there's one more important thing that I should, well, there's probably a couple more things I should talk about, but so far we've been talking about using the Euler-Lagrange to find the minimum of an integrand, which it can do, but really we should remember that this is giving either a maximum or a minimum. We don't know which, or something that's also neither, if something goes to a constant. But really what we're doing is we're going for the stationary solution. That's really what we're doing. And we're kind of reasoning that in this case there is a path that provides the shortest amount of time. There is not exactly a path that provides the longest amount of time, because the longest amount of time would be infinity, and it could just sit there and it would take infinity to get to P2. So, kind of have to look at it physically to figure out which of these that you're getting when you're getting your stationary solution. So the question is here, how do we know that our solution to the Euler-Lagrange equation is the minimum? And I'll just point out it is, which it is, so it is the minimum time, and not the max. Okay. So I think that we sort of just talked through it. You sort of conceptually just have to look at it and say, oh, there should be a path for which this is a minimum time. The path for which it's maximum time, there's many paths in which it can just sort of sit at rest for infinity and never get to P2. So minimum is the thing that is defined for this system. But sometimes you have systems where that's not the case. For instance, let's say that we had we wanted to go and we were on a sphere, the surface of a sphere, maybe like being on the Earth. And you wanted to get from point 1 on the sphere to point 2 on the sphere, but you were confined to traveling along the surface of the sphere. There is a path which is the longest, which is the shortest path. And that path, we could do this for. I mean, in that case, we've got sort of 3 variables for location. We usually pick x, y, z. But in this case, we would just notice that it makes more sense to use spherical coordinates. R is a constant, so we really just have theta and phi. And you can sort of set it up however you wanted to. You could have it as theta, theta prime, and phi as your 3 variables and solve for which path gives you this stationary solution. Now you should know in that case you're going to actually get 2 solutions. One will be this guy here, which is your shortest path. And it's called a geodesic. And it will be a portion of a great circle, meaning it's a portion of a circle whose center is at the center of the Earth. Okay? There will also be this path that you get that goes like this. Down the backside. Hold on, if I can do this. There will also be that path for which you get a value of 0, and that is the longest possible path. Which is also a portion of the exact same great circle. Both of these are portions of a great circle. Great circle just meaning it is a circle whose center is the center of the Earth. All right, that contains these 2 points. All right. So in that case, we would get 2 solutions, and we would need to notice that one is the minimum and one is the maximum. Obviously, the shorter one's the minimum. All right, so we're just going to have to consider conceptually which stationary solution it or they are when you get your solutions. Stationary solution. To determine whether it is a min or a max or, just one of those things that heads to a constant. All right. So one last topic in this chapter that we're going to discuss in detail is when we do have more than 2 variables, because all the problems that we've talked about, we've been able to break it down into 2 variable problems, even including this one here, which I didn't do explicitly, but you get the idea. Now and then you might need more than 2 variables. Alright, and when that's the case, what we're going to have to do is we're going to have to think, well, let's say that I have 3 variables. I can write one variable as a function of another, and I can write another variable as a function of that same other, so that now I have these 3 variables. And obviously in this case, u is my independent So now I have two dependent variables, one independent variable, and obviously I will also have two derivatives of dependent variables. So I have to, all right. And in that case, what we would have, like let's say we wanted to consider a length, maybe finding a minimum or length, something like that, we would again have some sort of an integral over ds, which would be still a square root of dx squared plus dy squared, meaning y prime squared plus x prime squared respect to u times du. And that should be squared. Sorry. Alright, so this would be the expression that you would get. Alright, in this case, we would still have this overall integral, which we should, understand. It goes from u1 to u2. It is, that integrand is a function of x, which is a dependent variable on u, y, which is a dependent variable on u. We've got dx du, dy du, and obviously u, which is the independent variable. And I have to integrate over du. So in this case, this would be the function. But you can imagine other situations. In that case, our Euler-Lagrange equations have the following form. Let me just go ahead and point it out to you. df dx is equal to partial with respect to u df dx prime, and df dy equals partial with respect to u df dy prime. Alright. Okay. That's not something that I want you to apply at this time. That's just something I want you to have some background in, so that when we start our next chapter and we start talking about Lagrangian mechanics, we kind of sort of have that in there, the idea that we could know what to do if there was more than just a dependent and an independent variable. Okay. So that's everything in terms of what I want you to get out of this chapter. It's really just kind of a math chapter, so I'm just sort of giving you guys the background that you need in order to do the physics that is coming up in the next chapter. So starting tomorrow, we are going to be doing Lagrangian mechanics. So that's chapter 7, so please read it if you haven't read it already. I'll see you then.